Hello, Science Wizards! Welcome to a new episode of Science Opener. On this episode, we will talk about photoelectric effect, specifically when and how does it happen. Then, we will work on some problems regarding on how to get the energy of a light in order to tell whether it can cause photoelectric effect or not. And lastly, we'll work on how to get the maximum kinetic energy of a photoelectron. So without further ado, let's start. In the 17th and 18th century, there was already an ongoing debate regarding on what really is the nature of light. Is it a particle or a wave? Until the 19th century, when Thomas Young conducted his experiment, also known as the double-slit experiment, which proved that light is a wave. And James Maxwell also proved that light is an electromagnetic wave. However, on the 20th century, Albert Einstein conducted this experiment which is known as the photoelectric effect, which also proved that light can be a particle. And light actually is composed of tiny particles which is called photons. According to Einstein's photoelectric effect, when a light shines through a metal surface, electrons from it can be actually ejected. However, in order to do that, the incident light must have sufficient energy to dislodge the electron from the metal surface. This minimum amount of energy required to dislodge the electron from the metal surface is what we call as the work function of the metal. So let's take a look at the quantum level and see how actually photoelectric effect happens. So from this illustration, we can observe that when a photon from an incident light hits an orbiting electron from one of the atoms in the metal surface, the electron will be ejected if the photon has an energy that is equal or greater than the work function. And take note that all of the energy of the photon absorbed by the electron is first used to free the electron. Any excess or remainder energy will be then converted as the kinetic energy of the photoelectron or the ejected electron. But you might ask, how can we know the energy of a light in order to tell whether it can cause photoelectric effect or not? Well, that's a good question. So in order to calculate for the energy of the light, we will use the formula E is equals to the Planck's constant multiplied to the frequency of the radiation. And this frequency of radiation is also equivalent to the speed of light divided to the wavelength of the incident light. And if we substitute this value of the frequency of the radiation here, we will arrive at a formula like this, where the energy of the light is equals to the Planck's constant multiplied to the speed of light over the wavelength of the incident light. So this is the formula that we are going to use in order to find the energy of a particular light and tell whether it can cause photoelectric effect or not. So let us use this formula in order to know whether there will be a photoelectric effect that will happen if we try to shoot a UV light onto a uranium metal with a work function of 3.6 electron volts. So let us go first with the given. So what we have here is the constant values for the Planck's constant and the speed of light, which is for the Planck's constant, it is equivalent to 4.14 times 10 raised to negative 15 electron volt seconds. And for the speed of light, we have 3.0 times 10 raised to 8 meters per second. And for the wavelength of the UV light, we will have 200 times 10 raised to negative 9 meters. Or in nanometers, it is equivalent to 200 nanometers. But for the sake of this problem, we will use the value of the wavelength of the ultraviolet light, which is in meters. So let us now proceed with the equation and substitute the values. So we will have 4.14 times 10 raised to negative 15 electron volt seconds multiplied to the speed of light, which is 3.0 times 10 raised to 8 meter per second divided by the wavelength of the UV light, which is 200 times 10 raised to negative 9 meters. So what we will do now is to cancel same units. So we will cancel the unit for the length, which is meter, and time, which is second, and what will be left is electron volt. So if we multiply these two factors, we will now have 1.242 times 10 raised to negative 6 electron volts over the wavelength of the UV light, which is 200 times 10 raised to negative 9. And if we divide these two values, we will get 6.21 electron volts. So this is the energy of the UV light. So if we compare it to the work function of the uranium metal, we can observe that the energy that a UV light has is greater than the work function. So we can conclude that there will be a photoelectric effect that will happen. Since we found out that the energy of the incident light or the UV light, which is 6.21 electron volts, is greater than the work function of the uranium metal, which is 3.6 electron volts, we can calculate for the maximum energy, kinetic energy, of the photoelectron or the ejected electron. So we will just simply use this formula, which is the maximum kinetic energy is equal to the energy of the incident light subtracted to the work function. So we will have 6.21 electron volt minus 3.6 electron volt. So this will be 2.61 electron volt. But since we are talking about kinetic energy, our unit must be expressed in joules. So we will convert this 2.61 electron volts into joule. So we know that 1 electron volt is also equivalent to 1.60 times 10 raised to negative 19 joules. So with this, we can now convert electron volt into joules. So let's cancel the unit of electron volt, and what we will have is the unit of joule. So we will just simply multiply these two numbers, and we will get 4.176 times 10 raised to negative 19 joules. So this will be now the maximum kinetic energy of the photoelectron or the ejected electron. 4.176 times 10 raised to negative 19 joules. So that is all for today, Science Wizards. I hope that you learned something on the concepts of photoelectric effect. So see you on the next episode of Science Opener. Keep safe and happy e-learning.